Welcome back to Data Every Day. Today we'll be looking at a dataset of healthcare analytics, which, if we just take a look at the trained data CSV, is basically a bunch of statistics about each patient. And if we look at the total columns, we can see at the end there's a stay column. And this is what we're going to try to predict, which is based on the conditions of the patient, how long will their stay be. And it's divided into 11 different categories of number of days. So 0 to 10 days, 41 to 50 days, etc. Let's get into it. I'm going to start with our usual libraries here. Let's import those, and we're going to load in our data using the pandas read CSV function. And when we get over here, the data file path. So trained data is what we'll use. And run that. Okay. And take a look. You can see this is what we're trying to predict, and this is the rest. And there's a lot going on here. This is not such a clean data set. Like, it's not ready to put into our model right away. We're going to have to be performing some pre-processing on it. So why don't we go ahead and mark that down. Pre-processing. The first thing we want to do is obviously check for any missing values. So missing values, I want to get rid of those in whichever way seems appropriate. So we can check the total number of missing values in each column. This will give us, the isNull function will give us a matrix or data frame of true or false values, where a value will only be true if that particular value is null. And let's go ahead and sum across the columns, or across the rows, so we get the total number of null values in each column. And you can see there's only two columns, bed grade and city code patient, that have any null values. So what we should do is figure out what is the data type of those columns. So bed grade is float, and city code patient is also a float. So that's very useful. Since they're floats, we don't have to worry about coming up with creative solutions. All we have to do is fill in the null values with the means of those respective columns. So to do that, we'll just make a quick function called, we'll call it impute means. No, impute missing values, we'll call it. And it'll take in some data and some list of columns. And basically for each column, we're going to set that column in the data to be the same column but with the null values. That's what the fill any function does. It will fill the null values with the mean of that column. So this will take, for example, the columns we'll pass in here will just be bed grade and city code patient. So for example, of bed grade, where column is bed grade, this will take the column of the data, fill it with the mean of that column, and then store it back in the original column. So we'll run that, and we will create a list called impute columns, and it's just going to be bed grade and city code patient. And then all we're going to do is run impute missing values on those columns. So we pass in the data we have and impute columns. Run that. Now if we take another look at this, there are no more missing values. So that's fantastic. What do we have to do next? Let's think. I think the first thing to realize is if we're going to put this into our model, everything has to be in numerical form. So we need to find all the data types of each of these columns so we know which columns to treat in which ways. So we'll call it data.dtypes. Will give us the list, or it's technically an object, I'm not sure what kind, of all the data types for each column. Yeah, can we check it? Does it have a type method? No, it doesn't. Okay, so let's see. Why don't the integer columns and the float columns are already dealt with. It's only these object columns that have strings in them that we have to deal with and convert to numerical values. So I think what we should do is let's make a function that's going to get all the unique values of each of these object columns. So we'll call it get categorical uniques. And it will take in the dataset. And the first step is going to be, let's figure out which of the columns are categorical. So we'll say categorical columns is going to be a list. I'm going to use list comprehension here to say every column for each column in data.dtypes dot index. So if we look at data.dtypes dot index, it'll just be a list of all of the names here. So without all of these names. So without the actual data type. So because we want the column name to be one of those names, we'll use the dot index to get these guys. And we only want to get that name if data.dtypes of that particular column is equal to object. So this is saying, alright, we're going to make this new list, and we're going to populate it with every column in the index of dtypes, so every column name, we should say, but only if that particular data type is an object. So this will give us a list of all of the column names with object data, or string data. And then we're going to make a dictionary. We'll call it categorical uniques. And this is going to be, we'll use the dictionary comprehension here to say we want a dictionary that matches a column name to the unique values of that column. So note, if I use this .unique function, let's say we want to use it on the word type column. Data word type .unique. It's going to give us a list array of all the unique values in word type. You see? So it goes through, finds all the unique values, and returns them here. So for each, we're going to make a dictionary that matches the column name to its respective unique values. And we're going to say for every column in categorical columns. Because we only want we don't care if it's a numeric column, right? We only want the ones in the categorical columns that have objects in them. And then just say return categorical uniques. Alright. So now, let's see. Okay. Let's call get categorical uniques on the data. Alright, and this is a very sort of difficult to read. It's all a bit sloppy, but if you look, each line is essentially a different dictionary entry that matches the column name to the list of unique values in that column. And so what we want to do is we want to figure out which of these columns need one-hot encoding, and which of these columns need some sort of ordinal coding or label encoding. So if we can find an order of the values, then we won't want to one-hot encode it. We'll want to label encode it. So let's take a look. Is there any order to the hospital type code? I don't think so, right? It could be of any one of these types, and no one type comes before the other, so this will be one-hot. The region code, the same thing, also one-hot, because there's no order between them. The department, no order. Radiotherapy is not better than surgery, or greater than surgery, or less than surgery. This is just, they're all separate, but not ordered. So also one-hot. These three are one-hot so far. Ward type, also one-hot. There's no order here. Ward facility code, also one-hot. There's no order here. Type of admission. Now this is an interesting one. You could say there's an order here. It makes sense to say that emergency is more urgent than urgent, and that urgent is more urgent than trauma. So we could order this: trauma, urgent, emergency. Instead of using one-hot encoding, we could then label that 0, 1, 2, and then use that as our new column. With severity of illness, also can be ordered. We can say minor, moderate, extreme in that order, 0, 1, 2, like that. For age, these are age groups, starting low and going to high. We can order this too. So this will not be one-hot. And finally, stay can also be ordered, because it's numerical values in the form of strings. So essentially what we have is all these will be one-hot, and all the rest will be label encoded. So what if we specify the one-hot columns? One-hot columns. It's going to be a list of all the one-hot columns we have. And just to save on some time, I have them all here. There. Just those 5. These first 5. Type of admission, severity of illness, age, and stay are not included here. And we're going to write a function. And before I do this, let's just mark down here. Since we finished with the missing values, this will be encoding. Okay. So we'll write a function. Call it one-hot encode. That takes in some data and a list of columns. Here our list of columns will be the one-hot columns. And what we're going to do is for each of those columns, we're going to create a dummies matrix. And we use the pandas.getDummies. There. And what this does, if we just take a look at that, replace column with, let's say, department. Ooh. This will take each unique value and create a new column for it, and return for each example all zeros with a single 1, depending on what the original value of that example was. So for example, example 0 has a 1 in radiotherapy. That's simply because if we look back at the original dataset, example 0 had a radiotherapy value for department. Another example, we can see this 318.434 had anesthesia as its department. And if we look down at this guy, the dummies matrix, 318.434 has a 1 for anesthesia and a 0 for everything else. So with this dummies matrix, you can see now it's in numerical form. So all we have to do is use this as our data instead of the original column. So we create this dummies guy, and then we're going to want to concatenate this dummies matrix onto our original dataset. And we use pandas.concat, and the list of data frames that we want to concatenate is data and dummies. Okay, and we want to specify that it's on the column axis, and that will just be our new data. And then, last step, we want to drop the original column. So drop column off the first axis, in place is true. Then we return data. Alright, so now we're going to pass in our one-hot columns as columns to this function. And so data is now going to be a one-hot encoded version of data and one-hot columns. Run that. Oh, we never ran this. Okay, take a look at data. Now we can see all those original columns are gone. For example, these in particular. So you can see department is gone, word type is gone, hospital type code is gone. All these are no longer in our dataset, and they've been replaced with their respective dummy values. And if either any two of these contained duplicate values, we would actually have to process them further so that we wouldn't have duplicate column names. What I mean by that is if one of the unique values in here is equal to one of the unique values in here, then when we created dummy matrices of them, we would have two columns with the same name, and that would cause some problems. So luckily, the people who made this dataset, very kind, made sure that each of these categorical columns have absolutely unique values from one another. So we don't have to worry about that. So next is the label encoding. We finished the one-hot encoding, and now we're going to let's take another look at our categorical uniques, which we have a function for that, get categorical uniques. It's the one we made earlier of the data. And you can see now we only have 4 categorical columns because all the rest have been converted to one-hot. So these 4 are going to be our ordered 4. We have type of admission, severity of illness, age, and stay. And these guys, okay, note that we could actually sort these guys. We can use Python sorted function to sort some list 271. We'll return 127. You see, and if we actually made these strings 0, 72, -4, it will also sort them as strings. If we have some words in there, you can see it will sort the numbers first and then the words after. So this is actually really useful because a lot of these are already ready to be sorted. Even this guy, you can see he has numbers as the first character. The first character is what matters in a string. And then there's this, which starts with an M, but that's actually supposed to go at the end because it's the greatest value. So we can just use sorted to sort this and then process it after that. These guys are going to need some additional processing. But let's go ahead and just sort this, sort every one of these. So what we'll do is we'll say for column in, and let's just store this in a variable called categorical uniques. Okay. So now we have this variable for it, and we can say for each column in it, in categorical uniques, we're going to sort that column. So categorical uniques indexed at the column is going to simply be equal to the sorted version of that. Okay, so this will sort it for us, and then we take another look at categorical uniques, and this is the version of it that we stored in the variable. You can see, okay, now it's in a list form instead of a NumPy array, so it's easier to sort of get a visualization of, and it has all been sorted. So this is exactly as we want it, right? This is going in ascending order. This is exactly as we want it, also going in ascending order. However, these two are not in order. So we'll just manually shift their values around. And to do that, we can just say, alright, we're going to want to process each column separately. So let's just, for the sake of convenience, make a variable called unique list, which will just be the first we will make it equal to categorical uniques indexed at there, and then later we will use it to mean severity of illness. So for this one, we're going to shift these values. All we have to do is bring urgent to the front and then trauma to the front so that it goes trauma, urgent, emergency. And to do that, we can take our unique list, which is this guy right here. And this is just a reference to it, so we can actually modify it. And we can call the insert method on there, which will insert at the 0th position, so at the very front of the list. The value to be inserted is going to be urgent, right? We're going to take urgent, move it to the front, then we'll take trauma and move it to the front. And then we'll have assorted in the way we want. So what we'll do here is we can take our unique list and just pop off the urgent value. And what that's saying, we'll pop it off and then we'll insert it at the first position. So it's doing two things in one line here. And we actually have to index it here. We can't just pop a word because this is a list. We have to pop a index. So we can say we'll actually pop unique list dot index at urgent. And so we'll do that for urgent, and then we'll do that same thing for trauma. And so this will take urgent, pop it to the front, trauma to pop it to the front, and then we'll do the same thing, except now we'll say unique list is severity of illness, and we want to bring moderate to the front and then minor to the front. So it goes moderate, it goes minor, moderate, extreme. So we can use these same two lines of code since we're still using unique list, and this will be moderate and this will be minor. So this will pull moderate, so it'll go moderate, extreme, minor, and then we'll pull minor, so it'll go minor, moderate, extreme. And if we just run that and take another look at categorical uniques, now trauma, urgent, emergency is in the proper order, minor, moderate, extreme is in the proper order, and these two columns are also in the proper order. So now we are ready to convert these into label encoded values. So just note, before we do that, I actually want to save the values that these are mapped to. Because later, since this is what I'm predicting, I'm going to be predicting one of these 11 classes, I want to know what the numerical values of those classes mean. Because we'll lose the information, like more than 100 days will just be converted to 10. So we just want to remember that 10 means more than 100 days. So we'll call stay mappings will be a dictionary, and the dictionary will be filled with mappings from one of these values to its numerical equivalent. And so if we have an index value pair in the enumerate of, what are we enumerating? The actual, right, so this thing, we want to enumerate this. So what that'll do is it'll give us an index and a value for each one. So categorical uniques indexed at stay. If we enumerate that, we can get an index value for each one, and then we can store each of those with a flipped version, value to index. So this is saying we'll get the index and the value for each one of these entries. So for example, this will be 0, this will be 1, this will be 2, this will be 3, and that will be index value, and we'll flip it so that we'll get a dictionary that matches a value 0 to 10 to an index 0. And just to take a look at what that looks like, we'll say stay mappings and look, and just as I explained, you can see now each one has a numerical equivalent, and we've saved it in stay mapping, so if we ever need to reference it again, it's right there. Okay, so let's do some ordinal encoding now on these guys, given their given the orders that we assigned them. So we'll make a function called ordinal encode, and it will take in some data and a set of unique column names, which we'll call uniques. And essentially, what we'll do is create a for loop for each column in uniques. So for each unique column, which is one of these, right? Let's just say here, so we can actually, one second. Okay, yeah, no. So the unique values we're passing in here will just be this, the categorical uniques, the dictionary. And we will basically say, okay, for that column, so we're iterating through the columns in there, which will just be the column names, right? Because this is one of them, this is another. As we iterate through, we're just getting these column names here. So for each column name, we'll get that data, the actual column, and we'll use apply to map a function onto every element in that column. And the function we're going to map is going to be taking some x, and it's going to return the index, right, of that value in our dictionary. So here's our dictionary, which is uniques that we passed through, and we'll find the value associated with it, right? So for example, if we had 21 to 30 as our value, as x, right? Let's say x is 21 to 30. That's one value in stay. Then 21 to 30 gets mapped to the index, not the index, 21 to 30 is the index. We will get the index of 21 to 30 within the unique list for stay. That was hard. Okay. So what that means is if we have stay as our column, right? Uniques as this whole thing, and x as a particular value that we're looking for. Let's use 21 to 30 as an example. Then we'll find a unique subcolumn. So what that's saying is unique substay, which is just this guy. And then we will get the index of our x. So our x is 21 to 30, so it finds the index, which is 0, 1, 2. So our value is 2. And what we're doing is by applying it, we're actually changing the value of 21 to 30 to 2. And we're going to do that for every value in column. Alright, so that will be our function. And we'll just take a look at the data one last time, especially the state column, just to see what it looks like before we do this. And then we'll call ordinal encode on our data and categorical uniques. And then we will take another look at the data, at the state column actually. You can see, oh, something went wrong, but looks like, oh, I know what happened. I didn't actually set it. Okay, so this was, it was just generating it and wasn't returning it to anything. Now it'll actually change the data. So we'll do that one more time. And you can see now everything has been mapped to its numerical value. 0 to 10 gets mapped to 0, 41 to 50 gets mapped to 4, and so on. And you can see that these mappings are actually what we defined right here. Right? So, I guess we're probably done. Let's look at the data types one more time, and actually let's find how many more string data types we have. So let's find, of all the data types, how many are equal to object. Sum it up. Oh, sorry, this it should be data. I have trained data in my other notebook. 0. So we're completely done with we are fully numerical now. And just take one last look at data. It is all numeric. Okay. So now let's scale our data. Scaling. And here, I'll just move this down here. Basically, we're going to create a y value, a y column, and an x data frame. So y is going to be what we're trying to predict. So it's just going to be our state column, and x will be everything except the state column. Okay. So run that. Take a look. Y is just one column of the values for stay, which again have been converted into numbers, and x will be everything except stay. So now we're going to import a few things. First, the scalar, which we're about to use. From sklearn.preprocessing, import standard scalar. And then we're also going to use a function from sklearn from model selection, import train test split. This will just make it easy to split our data. And then for the models that we'll use to predict, we will use logistic regression from sklearn.linear model, import logistic regression. And we will also use a TensorFlow neural network to do the same thing, but hopefully with a little better performance. Alright, so import that, come back down. Now we can scale this x. So we don't need to scale y because it's our classifications, right? But x is going to be, we want it all to take on similar ranges of values. Oh, and you know what I just realized? Case ID needs to be the actual indices here. So what we can do then is, how do we do this? There's a method, pandas use column as index, set index. So let's see, how does it work? Set index month. Okay. Alright, so x dot set index case ID. And that now uses case ID as our index column. And that's what we need, because we don't want to scale the case ID, and we also don't want to use it in our data. So let's see, I just want to make sure that I followed through. No, okay, so I have to make x equals set index. I could probably do this in place, actually, but whatever. Okay, and then y, this is actually annoying. Let's do it first. Let's do data.setIndex. And let's try the in place. Case ID in place equals true. Okay, now we'll drop this and we'll split it. Now if we take a look at y, the index, right, the indices for y are still case ID, and for x, good, also. So all we did is we set the index first and then we split it. Okay. So now we'll scale our x. We'll create a scalar object, be a standard scalar, and we're going to say x is going to be scalar.fitTransform x. So this will fit the scalar to our data in x, and then transform x accordingly. So it'll find the range of values that a column takes on, and it'll squish it down to have unit variance for every single column. Okay, and then we just want to turn that into a data frame, because it'll actually return a NumPy array, which we'll lose these column names and the indices. So to retain the column names when we create the new data frame, we'll just say that the index is going to be equal to our old index, and our columns will be equal to our old columns. Alright, run that, take a look at x. Now everything is as it is. We have the same indices and columns, except everything is scaled. Each column is scaled to have unit variance. This will make it easier for our models to work with. Alright, and now we will train our models. So first we'll split it between a train and test set. Xtrain, xtest, ytrain, ytest equals train test split x and y with a train size of 80%. And yeah, let's run that. And then we're going to make two models. First, our logistic model, we'll call it, will be the logistic regression that we imported from the sklearn, and we'll fit that to our train set. Oh, sorry, it should be log model. Okay. So that's fitting, and while that's fitting, I'm going to do a TensorFlow model, which takes a little more setup. We'll construct it by saying the layers. This is a neural network input layer to start, and the shape will be the a vector of the size of our column, so 38. And then our next layer will be tf.keras.layers.dense, which is a fully connected layer, so with 16 nodes and a ReLU activation. And we'll pass in inputs. Then our next layer will be the very same thing, and our output layer, outputs, will be tf.keras.layers.dense, and the number of nodes will be the number of classes we have, which is 11. So we're trying to predict 11 different unique values of stay. And the activation here will be softmax to return probabilities for each class. Oh right, and up here we should be passing in x, not inputs. Alright, then we make our model, which is a tf.keras.model with our inputs specified as above and our outputs as well. Run that. Shape is not defined. Oh, I didn't put equals. Okay. Now we'll compile that model. Optimizer is Atom. Loss, sparse categorical, cross entropy, which which is great for multi-class classification. And our metrics will just be accuracy. Alright, we'll compile it, and now we're ready to train it, fit it. So batch size is 32, and the number of epochs we'll train for, we'll say 10. And then history will be the history of our model's performance. We shouldn't call it model, let's call it neural network model, an N model, because we already have another model above. An N model, run, and then we'll fit it to xtrain, ytrain. We'll give it a validation split so we can see how it's doing. A batch size of batch size specified, epochs given by the epoch specified, and that should be good. Alright, we'll fit that. Now it'll take a little longer to train, but while we're doing that, we will plot the loss of this guy. So we'll give a figure size of 12 by 10. 14 by 10 sounds good. And then we'll plot on the x-axis a range of the number of epochs. And on the y-axis it will be the list of loss values in our model's history. We get that with .history indexed at loss. And then we'll just say the label for this is training loss. And we'll do the same thing for the validation loss. Then we'll give it an X label, which is X is showing number of epochs. And this one is showing our loss. And then we'll give it a legend as well. The location in the upper right. Okay. And just in time, this is finished. And we will, before I plot it yet, let's actually just take a look at how our models did. So our log model, which is our sklearn logistic regression model, we'll get the score of it this way, and we'll just we'll print that. So logistic regression accuracy, and then we'll do the same thing here, except this will be our NN model, and we use the evaluate function, and this will be neural network accuracy. Okay, and we actually should realize this thing to avoid the clutter, verbose 0, and this will return two values, the loss and the accuracy. We just want the accuracy, so we'll index it 1. Alright, so let's print that. And you can see our neural network did slightly better than our logistic regression, but these accuracy values are actually pretty in line with what other people have found. You can see 40, someone got 46 actually, 42, so we didn't do too badly. The dataset is probably just not very predictive of how long the patient will stay. But let's take a look at, maybe we can improve this a little bit. So if we plot that, this shows our training loss and our validation loss over the epochs. And you can see that our validation loss, our training loss always goes down, But our validation loss at some point starts going up again. And that's because the model starts to overfit. If you train any model long enough, it will start to overfit. So, which means it'll memorize our data set. And the training loss will keep getting better, but the validation loss will get worse. However, interestingly, we noticed that this is probably lower than this. So let's take a look at the minimum value here. So the minimum argument, this argument will give us the epoch, which gave us the minimum validation loss. And since it's actually a range of epochs, we have to do +1 because it'll start at 0. And you can see epoch 10 gives us the least validation loss. So, I think in practice we would want to run this for a little longer and get more of a sense of when the validation loss really starts to go back up. And then we would just train our model long enough so that we could achieve this lowest value. Here it happens to be 10, but let's say if it happened to be 6, we would retrain the model only for 6 epochs and then stop it there so that it has the highest accuracy possible. Alright, I think that sums up today's video. I know it was a long one, but I hope you liked it. If you did, make sure to subscribe and hit the bell and leave any comments below with suggestions for the channel, and just tell me how you liked the video. So thanks a lot. I'll see you guys tomorrow. Have a great day.